So today our topic is switch debouncing and interrupts. What is debouncing? When the state of a mechanical switch is changed from open to closed and vice versa, there is often a short period of time when the input voltage will jump between high and low levels a couple of times before it settles at the applied value. These transitions are called debouncing, and the getting rid of the effect of transitions is called debouncing. If you want to input a manual switch signal into a digital circuit, you will need to debounce the signal. So a single press does not appear like multiple presses. Alternatively, when a mechanical switch is flipped or pressed, the metal contacts inside may not open or close cleanly. In the microseconds before the switch achieves a good solid connection, the switch contact may bounce against each other, turning the switch on and off in rapid succession. So what happens when you press this manual switch? There may be effect of bouncing. That means we want a single effect from a single press, but we may get effect of multiple press. That's not desirable. It will cause malfunction of your electronic circuit. Okay. So why does bouncing happen? Bouncing is a result of physical property of mechanical switch. Switch and relay contacts are usually made of metallic springs. So when a switch is pressed, it is essentially two metal parts come together. This does not happen immediately. The switch bounces between in contact, close the contact, and not in contact. That means open the contact until it finally settles down. If you look at the picture, look at over here. You see, these are the bouncing. Sometimes it feel like switch is closed, sometimes it feel like switch is open. So a wrong signal will be supplied to the circuit. Okay, that is the switch. Okay. Certainly this is not desirable and we want to avoid it. Figure shows a simple push button with a pull-up resistor and its right side. The trace shows the output signal Vout when the switch is pressed. Look at over here. This is the mechanical switch, and when the switch is pressed, look at over here. These are the noise, high, low, high, low. Okay, before we get a transition from clean transition, we get multiple effect. As can be seen, pressing the switch does not provide a clean edge. Okay. If this signal is used as an input to a digital counter, for example, you will get multiple counts rather than the expected single count. Okay. So we want a single count, but what we are getting over here? Multiple count. Certainly not expected and malfunction. Right? So the same can also occur on the release of a switch. As you press and as you release, same thing can happen. The problem is that the contacts within the switch does not make contact cleanly, but slightly bounce. The bounce is quite slow, so you can recreate the trace and the problem quite easily. So with an oscilloscope, you can trace it. And look at over here, this is the oscilloscope output. Okay, from the mechanical switch. You can trace this problem in the oscilloscope. Why does bouncing happen? The bouncing phenomenon is associated with the single pole signal through that is SPST, single pole double through SPDT, and similar other types of toggle switches. The bouncing case data may be analyzed to see how long the switch bounce persists, how wide the individual bounce passes are, and how many bounces are observed. So you can use an oscilloscope to trace this bouncing effect. It is essential that the technique is not fooled by the occasional single glitch or spike caused by crosstalk, EMI, electromagnetic interference, RFI, that means radio frequency interference, ESD, that means electrostatic discharge. Okay. In this diagram, a resistor R1 is acting as a pull-up resistor. Look at over here. This is the R1. It's a pull-up resistor. This is a switch. And when the switch is open, R1 pulls the normally open contact to a positive value, usually 5 volt. When you close the switch, this goes to 5 volt. And we want to send this 5 volt to the microcontroller. And again, when the switch is closed, it is grounded. That means it shorts the no contact to 0 volt. That means it will send a 0 value to the microcontroller. But in reality, that clean transition does not happen. Look at the picture. Noise. Okay. So switch bounce may be removed by hardware before being presented to the microcontroller. So what we need to do, we can use a hardware circuitry to remove this bouncing effect before we feed this signal to the microcontroller. Or we can use a software approach. Switch bounce may be removed in software after being presented to the microcontroller. So before we can use a hardware, then send the clean signal, or after the microcontroller get the signal, we can use the software technique to remove the bouncing effect. So two techniques, software approach and hardware approach. When people push a mechanical switch button, they expect one reaction per push. As the buttons tend to bounce around when pressed and released, this will mess up the signal from them. Okay. For example, we have a button that is connected between a voltage supply and the output probe. Okay. We intend to get an output voltage of 5 volt, that is logic 1, when the switch is pressed, and 0 volt, logic 0, when it is not pressed. If we probed the output signal coming from the button during the transition from pushing it down to letting go, we expect an immediate and clean transition from 0 to 1 and 1 to 0. Okay. Press the switch, go to 1, release the switch, we want to go to 0. What we end up seeing instead of the picture above, okay, that means we end up like this. Instead of clean transition, we end up like this, noise. Okay. Before the signal settles to a fixed 5 volt, it bounces between the two logic steps several times. Okay. How to avoid bouncing? The digital functions in general and microcontrollers don't like to see input signals wandering around the undefined region between a good logic 0 and good logic 1. Okay. In 1934, a young graduate student named Otto Herbert Schmidt, okay, invented a circuit known as Schmidt trigger. This invention was a result of Otto's study into the propagation of neural impulses in the nerves of a squid, okay, a kind of sea fish. The best way to describe this is by means of a figure as illustrated in the next slide. So Schmidt trigger, how it does? Look at over here. This is the Schmidt trigger. We give the input signal, take the output. There can be a standard buffer with single threshold. Now, if we use a technique that if we use a single threshold, this is the threshold value. We define a threshold value that if the signal goes above the threshold value, it will be high or 5 volt. If the signals go below the threshold value, it will be 0 or 0 volt, okay, grounded, 0 volt. So in this case, look at over here. You see the signal going a single threshold, signal going up the threshold, it is 1. Signal is coming below the threshold, it is 0. Again, signal going up the threshold, it is 1. Signal coming below the threshold, it is 0. Below the threshold, 0, okay, and up the threshold, 1. So what is happening? As you see, with single threshold, we are getting wrong output. Multiple phase effect. Not good. So what we do in symmetrical, we use two threshold. One is the upper threshold, other is the lower threshold. Red color, you see, if you look at the red color is the upper threshold. And this green color is the lower threshold. Dual threshold, we call dual threshold. So if the signals cross the upper threshold, we'll treat as 1 or 5 volt. And if the signal crosses the below threshold, we'll treat as 0 volt. So what is happening over here? Look at over here. Let's analyze. At this point, look at over here. Signal is crossing the upper threshold. So we'll treat as 1. And this signal not crossing the lower threshold. So we'll not treat as 0. It's still 1. Till the signal crosses the lower threshold. At this point, look at over here. At this point, signal is crossing the lower threshold. So we'll treat this one as 0. So only when the signal crosses the upper threshold, we'll treat as 1. And only when the signal crosses the lower threshold, we'll treat as 0. So what is we are getting? A very good output, clean output. No noise. So symmetrical can be used in the hardware circuit to get clean output. With it has dual threshold. Okay. A standard buffer has only a single switching threshold, which means that a noisy signal, including a signal with a bit of ripple on it, can result in multiple transitions at the output, as we have seen on the last slide. In comparison, a symmetrical buffer, that is a buffer with a symmetrical input, has two thresholds. The output changes only when the input crosses the upper threshold or the lower threshold. The dual threshold action is called hysteresis, the dependence of the state of a system on its state, which implies that the trigger possesses memory. So in the RC network, we use a simple space switch debounce circuit. Look at over here. This is the simple circuit we use to debounce. Okay. And then a symmetrical buffer. This is the symmetrical buffer between the RC network and the microcontroller as stated below. So what happens? This circuit plus this one, they will make your signal a clean signal. A 0 is 0 and a 1 is 1. Nothing in between. Okay. So we have shown a non-inverting symmetrical buffer to keep things simple. All the signals going up and down in a common direction. It is common to use the inverting symmetrical because inverting functions are faster than non-inverting counterparts. Bouncing often causes problems in the application where pressing the switch once should theoretically cause only one transition. If we connect the switch button to a pin with an external interrupt enabled, we will get several interrupts from pressing the button just once. In the microcontroller, certainly your controller will be fooled. Okay. This behavior is normally not wanted and can cause multiple false button presses. Example. Yes. Imagine using a button in a TV remote controller for the selection of a channel. You are using the remote controller for the selection of a channel. You have pressed the button. If a single press skip many channels, certainly you will throw that remote. You will not use that remote, right? A single press will single transition from one channel to the next channel, okay? not multiple transition. Okay, so if the button is not being debounced, one press can cause the remote to skip one or more channels, not desirable. There are several different types of debouncing. Okay, situation way you can do. You can remedy this problem by debouncing the switch. There are many ways to do this. There are two general ways of getting rid of bounces. Hardware debouncing, adding circuitry that actually gets rid of unwanted transition. Software debouncing, adding code or program that causes application to ignore bounces. Digital switch debouncing, achieved in the same way as the software approach, and switch debouncer using VSDL. Okay, the VSDL entity description is used over here for debouncer. So there are several ways you can do it. This is the hardware debouncing circuit. There are various implementation of circuit that can be used for eliminating the effect of switch debouncing right at the hardware level. Before you feed the signal to the circuit, use the hardware, make the signal clean, okay, debounce it. One of the most popular solutions using hardware is to employ a resistor capacitor network with a time constant tau longer than the time it takes the bouncing contacts to stop. That means tau should be greater than bouncing time. During the time it bounce, so it will avoid that bounce. Okay. Often it is also followed by a symmetry trigger, okay, which helps get rid of capacitor voltage values midway between high and low value. Okay, symmetry trigger is mainly used to get rid of capacitor voltage because capacitor get charged and discharged. It takes time. Okay, capacitor get charged and discharged. That means when you close a switch, this voltage make the capacitor charged. Okay, next time it get discharged. Okay, so when you remove the switch, okay, the capacitor get discharged to the ground. So because of capacitor, we can use the symmetry trigger to make our signal more clean. If we wish to preserve program execution cycles, it is best to use the hardware debouncing approach because it will be the faster. It will not occupy the programming cycle. Okay, you use the hardware. Hardware approach is always faster. Why hardware approach is faster? You can tell. Let's say there's a rule called equivalence of hardware and software. Okay, when you design something in the computer or IT field, you follow a rule. The rule is called what you can do with the hardware, same you can do with the software, and vice versa. That means what you can do with the software, same you can do with the hardware. Now we have designed a device, for example, that one approach is hardware approach, one approach is software approach. Now my question is, which one will be the faster? Hardware design will be faster or software design will be faster? Software will be faster. Why? Okay, if a business student give this answer, okay, that's fine. But you are the engineering student. You need to explain why software is faster than hardware. So to understand this situation, you need to understand how things get work, how software works. There's a cycle called fetch, decode, execute. Software is essentially a program, right? Your CPU fetch the instruction, then decode the instruction, then execute the instruction. So it is a cycle called fetch, decode, and execute cycle. That's the way program works. Software approach. And what is the hardware approach? Action, action, direct action. Okay. Have you seen this voice on the street? When you protest, you tell, okay? Action, action, direct action. That's the hardware approach. No fetch and decode, only execution. Okay, only execution. So hardware approach is 2 steps less than the software. Now tell me which one is faster? Hardware is faster. But because nowadays technology is very advanced, your software runs very at high speed, the difference is coming down day by day. Okay, difference is very low, but still hardware is always faster because it is 2 steps less, right? So if you want to get a faster system response, use the hardware debouncing approach. Then your system will be faster. Okay, there can be many time critical application you need faster response. Then go for the hardware debouncing approach. Otherwise, for common application, you can go for the software. Okay. In hardware debouncing, we may use a flip-flop to latch the signal using a capacitor to absorb the bouncing period. Example circuit. Look at over here. In the next slide, there is a simple circuit for debouncing a switch for digital logic. When the switch is closed, the voltage is pulled down through the switch, and when the switch is open, the output voltage is pulled high through the resistor. Look at over here. When the switch is open, this voltage is fed. That means we expect high value. When the switch is closed, then it is grounded. We expect low value. So look at over here. This is the case without the symmetrical. This picture on the left is the case without the symmetrical, because of capacitor. Capacitor get charged and discharged. So with the symmetrical, we are getting clean transition. So what approach will take? A circuit with symmetrical, right? Because we see the clean transition. Okay, so look at over here. There is one problem. The capacitor exhibits a curve when charging, and parts of this curve will fall in the region where a logic chip is undecided whether to treat it as a high or low. To fix this, a symmetrical is added to the circuit. And what we say? Clean output. Okay, so that's the, I think, if you use the symmetrical with the conventional circuit, clean transition, right? Remember that the 7414 symmetrical will invert the signal. Okay. Look at over here. There is some formula. Circuit design using a 7414 is a symmetrical inverting type buffer with input hysteresis. So the equation for discharging a capacitor is given by this formula. Debouncing circuit design using the 7414 symmetrical. Okay, so this is the circuit. Okay, so as we see in the we get clean output. Okay, we get clean output like this with the symmetrical. The circuit operation can be explained by looking at the equivalent circuit formed in the two switching state, that is open and closed. Look at over here. Starting with the switch open. When the switch is open, what happens? The voltage VCC comes to the input of the symmetrical. And capacitor, look at over here. The capacitor C1 will charge via R1 and D1. This capacitor will get charged via R1 and D1. In time, C1 will charge and VB will reach within 0.7 volt of VCC. Okay. Therefore, the output of the inverting symmetrical will be logic 0 because it is inverting. When you give high value, you get low. So when you open the switch, you get a low value. Okay. When you open the switch is open, you get a low value. It's fine, right? And when you close the switch, we should get a high value. So now to close the switch, the capacitor will discharge by R2. When you close the switch, the capacitor will discharge by R2 through the ground. There's a grounded, this is grounded, right? So the capacitor will discharge by R2. In time, C1 will discharge and VB will reach to 0. This VB will reach to 0 because it is grounded. Therefore, the output of the inverting symmetrical will be a logic 1. That means when you close the switch, we should get a high output. When the switch is open, we should get a low output. And this is clean high and clean low. No noise. What about bounce condition? If bounce occurs and there are short periods of switch closure or opening, the capacitor will stop the voltage at VB immediately reaching VCC or ground. Okay, when there is a bouncing, then capacitor will stop the voltage at VB. That means the voltage at this point will get a stop because of charging and discharging. Okay, because capacitor cannot charge and discharge quickly. Okay, it takes time. Instantly, it cannot charge or discharge. It takes time. So the state remains at the same. That means if you want the open state, capacitor is ensuring it is open state. When you want the closed state, capacitor is ensuring that is closed state, because the voltage of capacitor cannot change instantaneously. It takes time. So that we take advantage of the property of the capacitor. Okay, that gives a delay. That means it avoids the bouncing effect. So the hysteresis of the symmetrical input stops the output from switching. Okay. What about the diode? The resistor R2 is required as a discharge path for the capacitor. Without it, C1 will be shorted when the switch is closed. Without the diode D1, both R1 and R2 would form the capacitor's charging path when the switch is open. The combination of R1 and R2 increases the capacitor's charging time and thus slows down the circuit. So if you don't use the R2 resistor, then it will slow down the circuit. However, when the switch is closed, R1 is connected across the supply rails to limit the current flow in the circuit. Okay, so we need this R2, otherwise it will slow in operation. Numerical example, okay, a CMOS device like 74AHCT14 delivers about an milliampere from the input. Both R1 and R2 control the capacitor charging time and so set the debounce period for the switch open state. The equation of charging the capacitor is this one. Okay. The main thing, main concept, capacitor helps to hold the state. Okay. So during it bounce, it avoids that bouncing effect. It holds the state. The goal is to select values that ensure the capacitor voltage stays above the V threshold, the threshold at which the gate switches till the switch stops bouncing. Okay. Most of the switches exhibit bounce time well under 10 milliseconds. So the use of this value would be a conservative choice. Now increase that by the bounce duty cycle. Based on experimental data, we can expect about a 50% duty cycle, giving us 20 milliseconds of time period. Using the time constant formula to solve for R, the cost and size of capacitors vary widely, so it is best option to select a value of C and then compute R. Okay, so first select the value of C and then compute R. We get the value of C and R. The AHCT version has a worst case V threshold for a signal going low to low of 1.74. Let us try with a 0.1 microfarad capacitor, since this is a small chip, and solve for the conditions in which the switch is closed. The capacitor discharges through R2. If the power supply is 5 volt, okay, then we can calculate R2. So for a capacitor of 0.1 microfarad, this is cheaper version, cheaper one, we get R2 is 185 kilo. Okay, by using the formula. Since a resistor with this value is not available, we use 180 kilo. Okay, closed value. This is not available. That means 185 is, I think, is not available. The closest value you need to take. If you can get 185, fine. But if you cannot get, go for closest choice, 180. But the analysis ignores the gate's input leakage current. A CMOS device like the 74ACT14 reverts about a microampere from the inputs leakage current. Okay, that 180 kilo ohm resistor will bias the input up to 0.1 volt. Okay, by using the formula V equal to IR because of the leakage current. Okay, uncomfortably close to the gate's best case switching point of 0.5 volt. Therefore, change the capacitor's capacitance to 1 microfarad and use 80 kilo ohm for output. So what happens in this for to best effect? We use 1 microfarad capacitor because of the leakage current and use 18 kilo ohm for output. If we consider the leakage current, okay, that's the best scenario. R1 plus R2 controls the capacitor charging time and so sets the debounce period for the condition when the switch opens. The equation for charging, this is the equation for charging, okay? Solving for R, so what we get? V final is the final charge value of the 5-volt power supply. V threshold is the worst case transition point for a high going signal, which for our 74ASCT14 is 0.9 volt. So R1 plus R2, what we get? By using the formula, 100 plus 78 kilo ohm and R2 is 18 kilo ohm. So R1 is 82 kilo ohm. So by using the formula, when you take account of the charging leakage current, we find that okay, this is our suitable value. R2 is 18 kilo ohm, R1 is 82 kilo ohm, and what is the capacitor? 1 microfarad capacitor. Okay. The diode is an optional part needed only when the math goes haywire. Okay. It is possible with the wrong sort of gate where the hysteresis voltage assume other values for the formulas to pop up a value of for R1 R2 which is less than that of R2. Okay. The part forms a shortcut that removes R2 from the charging circuit. All the charge flows through R1. Equations will be same except that we have to take the voltage drop across the diode into account. Change V final to 4.3 volt, 5 minus the gate voltage, threshold voltage 0.7 volt of the diode's farad voltage drop and solve for R1. Be wary of the components tolerance. Standard resistors are usually plus minus 5 minus 10% and the capacitors are plus minus 20%. Okay, for electrolytic and plus minus 30% for a small ceramic capacitor are error prone from their normal rating. So debouncing in hardware may give rise to additional cost, as we see, and it is more difficult to determine a good debouncing for all the push button switches that will be used. So it may be preferable to debounce the switch in software. If your situation is like that, you're not getting good result from the hardware approach, go for the software approach. Debouncing a switch in software is very simple. Low cost alternative. No hardware is needed, so it is low cost. Only inside the program. The basic idea is to sample the switch signal at a regular interval and filter out any glitches. There are a couple of approaches to achieving this. These approaches assume a switch circuit like that shown in the explanation of switch bounce, okay, a simple push switch with a pull-up resistor. While numerous algorithms exist to perform the debouncing function, we are going to limit ourselves to implementing two during the lab. Both approaches uses a timer. Approach 1. Okay. The first approach uses a counter to time how long the switch signal has been low. If the signal has been low continuously for a set amount of time, then it is considered pressed and stable. So we use a timer and check whether it is maintaining the state or not. If it is maintaining the state for a fixed amount of time, okay, we are sure, okay, it is clean signal, okay, stable signal. So first set up a counter variable initialized to 0. Set up a regular sampling event, perhaps using a timer, okay, and use a period of about 1 millisecond sampling time, okay. So on a sample event, if the switch signal is high, then reset the counter variable to 0 and set internal switch state to released. Else, increment the counter variable to a maximum of 10 and NF. So within this count, we check, give a counting. That means even it will check, okay, 10 times or 5 times. Give a counting within this time period. Okay, let's say within 2 milliseconds or depending on your need, you will check how many times, 5 times, 10 times, or 2 times, or 3 times, depending on your requirement. Okay. So if the counter is 10, then set internal switch state to test. That means after checking several times within the time limit, if you think that okay, you are getting the same result, then that's the stable value. This is very simple approach. Okay, I think we have already simulated. I think we'll simulate these things in your lab using Proteus. You can do it. Okay, in Proteus already we have done the simulation, and I think you can use it in the lab. Very simple approach. We have used it in a previous lab sheet. Okay, other semester we have used this approach. And other approach, okay. The second approach is similar to the first, but uses a shift register instead of counter. The algorithm assumes that an unsigned 8-bit register value, which has as that found in 8-bit microcontroller. So in that case, over here, you just use the shift register instead of counter, but similar approach. Okay, and this algorithm given. Set up a variable to act as a shift register and initialize it to XFF. Okay. Set up a regular sampling event, perhaps using a timer. Use a period of about 1 millisecond. On the sample event, shift the variable toward the most significant bit. Set the less significant bit to current switch value. If the shift register value is 0, set internal switch state to pressed. That means using shift register is actually acting as a counter. You're shifting the bit one by one, and after you shift all the bit, if you get a fixed value on the shift register, that is a stable value. Either it can be 0 or it can be 1. Okay. So that's the shift register technique. There are 2 more approaches of software debouncing. The first technique, we wait for a switch closure, then test the switch again after a short delay, 15 milliseconds or so. If it is still closed, we determine that the switch has been changed state. In the second technique, we test the switch periodically to see if it has changed its state. Software debouncing, when working with a microcontroller, we can deal with switch bounce in a different way that will save both hardware, space, and money. Some programmers do not care much about bouncing switch and just add a 50 millisecond delay after the first bounce. This will force the microcontroller to wait 50 milliseconds for the bouncing to stop and then continue with the program. This is actually not a good practice as it keeps the microcontroller occupied with waiting out with the delay. So instead of using the delay function in your program, what you can do, you can use the timer approach. As we have seen in our last class, if you use the timer approach, then we can avoid the problem that associated with the delay function. Okay, when you use the delay function, everything gets stopped. Wait until the delay is over. But if you use the timer approach, then you don't need to wait on other jobs. Okay, other jobs can continue as you waiting for the switch to have a stable state. So that's the timer approach. Okay. So this is an example given with the timer approach. I think in our lab you will use the Arduino microcontroller at Mega 328P. In lab number 3, you will do it using the timer approach. And in your thing over here, they have used a click microcontroller. So those who are interested, you can just go through it. But in our lab, we'll use the Atmega 328P microcontroller, and we'll do it in the lab number 3, timer approach. So let's skip this one. Before we go to the next topic, I want to give you a short break. Interrupts. An interrupt is the automatic transfer of software execution in response to a hardware event that is asynchronous with the current software execution. The hardware event can either be a busy to ready transition in an external I/O device like the UART input or output, or an internal event like bus fault, memory fault, or a periodic timer. Let me give you a simple example. Suppose we want to implement a system, okay, that when someone enters the room, our AC will get turned on. When someone, that means when the room is empty, everybody leaves the room, the AC will be turned off. So, in software approach by using the microcontroller, how we do it? We use a sensor called PIR sensor to sense the presence of human. PIR sensor. So, how this sensor works? When the sensor senses the presence of a human, the sensor sends a high value to the microcontroller pin. So when we get a high value in the microcontroller pin, we take necessary action. That means we turn on the AC. Okay. Now, in conventional approach, okay, how we do it? We use a loop. Your Arduino program has two parts: setup and loop. In the loop part, we continuously check the pin value. Okay, whether it is high or low. If the value is high, we turn on the AC. If the value is low, okay, after we implement the mechanism. That means after the room is empty, we set up the code that when the room is empty, that means when no one is in the room, we turn off this when the value is low. Now, if we use the conventional loop approach, what happens? CPU will continuously monitor whether someone is in the room or not, okay, or someone is entering at the door or not. So, if I tell you, okay, you are the CPU, and when someone enters the room, you turn on this. Suppose you are doing the job. So, what you are doing? You are looking at the door all the time. Suppose in a day, no one has arrived. Okay, so you don't need to do any action. Still, you are checking the door, whether someone is on the door or not, or coming or not. So, what is the scenario? Even though it is not required, you are wasting your valuable time. You are wasting your valuable time. You are just looking at the door, waiting for someone to come, but no one came at that day. Let's say even a week, no one came. So you are wasting your valuable time and resource. So how to improve the situation? We use a technical interrupt. Instead of looking at the door all the time, what we do? When the event happens, that means when someone comes in the room, this PIR sensor sends a signal to the pin. When the pin gets the signal, it runs an interrupt service routine. So we don't use a loop over here. Instead of using the code inside the loop, what we do? We use interrupt service routine. When the event happens, it runs that interrupt service routine to perform action. So only when needed, you do the job. Otherwise, you do your other activity. That means the CPU can do other activity when not required. Only when needed, it will run the interrupt service routine to perform the job. Okay, so that's the advantage of using interrupt. Is that clear? So how we do it? Okay, there's an example given over here. Let's think about a real life example. You are heating up your food using the microwave. In this case, you can either stare at the microwave while it heats up the food, or second way, go about your life normally and go to the microwave when you get the signal that the food has been heated up. Which of the above mentioned options do you think is more efficient? First one or second one? You are staring at your microwave all the time. When the food is stuck, you take the food, enjoy it. Or give the food in the microwave oven and go for watching TV, go for other job. When you get the sound, okay, ting sound, okay, you come back, take the food, enjoy it. So which one you like? Second one, okay, that's the interrupt. Okay, so this is because we want to make efficient use of our time. It is very similar to processor as well. We hear the ting sound from the microwave, stop what you are doing and go to take out the heated food. This ting sound is an interrupt. Similarly, if the processor is waiting for some condition to be fulfilled to perform a specific task 1, okay, it can wait and halt other processes till the conditions for that task is fulfilled, like inside a loop. Okay, it will check again and again whether the task has been done or not. Okay, inefficient method, wasters of resource. So it can execute normal instruction and halt them for a brief time once the condition for task 1 has been fulfilled, finish the task 1 and go back to executing the main routine. So that's an efficient way. Interrupt approach. Clearly, the second option is better for maximizing the processor resource utilization. This is where interrupts come in handy. When the conditions for a task has been met, it can simply trigger an interrupt, stop the main routine to complete the task, and once finished, go back to the main routine. Interrupt conditions, there are several conditions like device arm, NVIC, enable, global enable, interrupt priority level must be higher than the current level executing, and hardware event trigger. Certainly, what you are doing in computer, there's concept of priority. Interrupt should be given higher priority than the normal execution. Otherwise, when there is an interrupt request, it will not give you the service. Because if your normal execution has higher priority, it will not bother that request. Okay, just a lower priority. So you must give the interrupt priority higher than the normal execution. To arm a device means allow the hardware trigger to interrupt. To disarm a device means that shut off or disconnect the hardware trigger from the interrupt. Nested vector interrupt controller, NVIC, the module that controls all the interrupts. NVIC is device specific. Global enable, this is like main switch. In every CPU or microcontroller, there is a register called flag register, and there is a bit called interrupt enable bit. This is like a main switch in your home. Okay, when the switch is on, main switch is on, interrupt is enabled. When the main switch is off, interrupt cannot take place. Okay, this is like main switch. Okay, global enable. Priority, interrupts have priorities. Suppose two different tasks must be done at the same time, then the tasks must be assigned relative priorities to decide which will be performed first. Trigger, an asynchronous event which causes the interrupt. For example, the push button pressed during experiment number 4 in our mesh lab can be a trigger. Okay, suppose when you use the push button, it will trigger some event. It can cause an interrupt which is registered by the module and is reacted to. However, what if all the conditions are not met but the trigger flag is set? In this case, rather than the requested being dismissed, it is held pending, postponed until a later time. If not all conditions are met, then postpone it for a later time when the conditions are met. What happens after a trigger? Once the interrupt is triggered and processed, the interrupt flag is cleared. Clearing the interrupt flag is called acknowledgement. Now, when there's interrupt request, every interrupt has an associated interrupt service routine. In this interrupt service routine, you define what to do. Okay, and it does only once. Okay, to perform the job. This is asynchronous. This code is not inside the loop. Okay, so it is outside the loop. This routine. The module that is executed when a hardware requests an interrupt. There may be one large interrupt service routine handling all the interrupt requests, or many small interrupt service routine handling the many interrupt. Okay, so these are the example. Remember, the ISI is a separate routine and requires a separate flowchart to represent. This is not part of the loop, outside the loop. Okay. General rules for ISR. The ISR should execute as fast as possible. The interrupt should occur when it's time to perform the required action. The ISR should perform the action. The ISR should end and return to the main function right away. Placing backward branches like BG, wait, and iteration inside the ISR should be avoided. The percentage of time spent executing ISR should be small when compared to the time between the interrupt triggers. Okay, these are important things. Now, final reference. And that's the end of the slide. Okay.